So a phase diagram is a little bit like a map of the state of a substance. State and phase are two words that refer to the same thing. What physical state, what physical phase is the matter in, solid, liquid, gas? And we look at what state it is in as a function of pressure and temperature. So we graph pressure on the y-axis and temperature on the x-axis. Let's just peek at one here. So this is a phase diagram for water. Typically these are not drawn to scale because they're just for general ideas. So here we have on the y-axis the pressure in torr, the temperature in degrees Celsius. And we see different regions here. So here, this region is labeled solid, this is labeled liquid, and this is labeled gas. If we identify a particular pressure and temperature, say atmospheric pressure 760 torr and 0 degrees Celsius, that's the temperature at which ice melts. And so on this graph, that will be on the line between a solid and a liquid. At 100 degrees Celsius, that point will fall on the line between the liquid and a gas. And so this line here represents vaporization. At atmospheric pressure, if we go above 100 degrees, the water will be in the gas state. If we're between 100 and 0, it'll be in the liquid state. If we are below 0, the gas will be in the solid state. So this is the fusion curve going from solid to liquid is melting or fusion. Here's our sublimation curve going from the solid directly to the gas. And then up here is the critical point. Above that temperature, you can't have a liquid. It becomes a supercritical fluid. And so this line just ends. There's a critical pressure and a critical temperature. Above that, you can't have a liquid. So the regions represent conditions where that state is stable. The lines are typically curves, represent a set of temperatures and pressures where that substance is in equilibrium, where it's undergoing a transition. And then we have what's called the triple point, and that's a unique set of conditions in which all three states are stable and in equilibrium. So for water, the triple point is here. It's at a lower pressure than atmospheric pressure, and it's just a little bit above the freezing point. But at that particular temperature and pressure, you will have a solid, a liquid, and a gas all in equilibrium. That just seems kind of crazy and impossible. And so I have a video here to show you. This is not of water, but this is illustrates a triple point of tert-butyl alcohol. I don't think there's any audio on this. So they've got a vacuum, and they're pulling a vacuum on this, and they have a thermometer in there to measure the temperature. So they're lowering the pressure, and they get to a point where it starts to boil. Because as you lower the pressure, the liquid will boil at a lower temperature. So there it is, boiling at room temperature. And now 30 seconds later, two minutes later, so it's freezing. We've seen the solid form, and it's boiling. What? It's boiling and freezing at the same time. You're welcome. Is that crazy or what? That is super crazy. That's the triple point. We don't observe this all the time because I don't know of any liquid or any substance, I should say, whose triple point occurs at like room temperature and atmospheric pressure. That'd be kind of trippy. Any questions? Why? How? Well, let's look at the phase diagram. So that was butyl alcohol, which has a different phase diagram, but it's still going to have a triple point like this. So if we took water at this temperature, I don't know what it is, it's like maybe 5 or 10 degrees, and what they did is they reduced the pressure. Of course, reducing the pressure can cause the temperature to change, but reducing the pressure, if we do that over here, we can cause the water to boil. And we just keep, if you keep reducing, it's just going to go into the gas state and you won't see the triple point. The triple point will only happen at this one temperature and pressure. But there is this point where all three of them are stable, where the sublimation curve, the fusion curve, and the vaporization curve run into each other. So you get all three of them. So we talk about navigation within a phase diagram. And generally we would do this in straight lines. And so you can either look at changes in pressure or changes in temperature. So here, line segment A, here we're at 1 atmosphere of pressure, going from minus 25 degrees Celsius up to, say, 125. So this is what we were looking at with the water when we were calculating the amount of energy. As we increase the temperature, we've got a solid, we get to a point where it melts. Now we have a liquid, we increase the temperature, it remains a liquid until we get up to the boiling point, and then it transitions into a gas. Okay, that's changing the temperature. If we pick a temperature, say room temperature, and change the pressure, we've got the liquid water, we decrease the pressure above it, it stays a liquid until we get down to this pressure, and then the water will begin to boil at room temperature. You keep reducing the pressure and you will have a gas. So this is one of only a handful of very clear memories I have of high school. It's a while ago, this is kind of a blur. But honors chemistry class. Beginning of one lecture, the teacher set up a big vacuum flask and with water in it and hooked it up to a vacuum pump, and it's sitting down there going chug, chug, chug. And then he's lecturing and explaining stuff to us. And after a while, it took a while, but after a while, the water in the flask began to boil. And there's no hidden heat source under the counter or anything. It's just sitting there on the bench. So the water's boiling, and he made all of us come up and touch it with our bare hands, the outside of the flask. And of course, the first person is like, I don't want to touch that, it's hot, right? Boiling water is hot. No, it was room temperature. It was boiling at room temperature. And that's one of those things that just like stuck in my head, because how does this even happen? Low enough pressure, water will boil at room temperature. Any questions? Different substances have different shapes to the curves in their phase diagrams. So here we have iodine and carbon dioxide. And notice that this fusion curve has a positive slope for both of these. When we look at the fusion curve for water, it has a negative slope. It slants the other way. if you have, let me see if I can draw a line that's going to work. So if you have solid ice, didn't mean to do that. If you have solid ice and you increase the pressure at a given temperature, you can cause the liquid to form. You can cause the ice to melt. This is how ice skates work. This is why part of why ice is so slippery. What an ice skate does is it takes all your body mass and distributes it onto a very narrow blade, which means that there's a lot of pressure on the ice. So a lot of pressure on the ice causes a layer at the top to melt, just from the pressure. And water on ice is especially slippery, and so the skates will glide. That can only happen because of this negatively sloped curve here. That's very unusual. Most substances are not like that. Iodine and carbon dioxide, if you take the solid and put pressure on it, it's just going to remain a solid. If you take the liquid and put pressure on it, it will become a solid. And so that's very different than for water. So for iodine, here at 1 atmosphere, it will melt. Well, here we've got the triple point for iodine. I forgot where I was going with that. I don't know. There's the critical point. So you've got supercritical fluid up here. Here's carbon dioxide. The curves don't necessarily look super different until you look at the pressures here. This is 72 atmospheres. That's a huge amount of pressure. That's the critical pressure for CO2. The critical temperature is 31 degrees Celsius, which is only a little bit above room temperature. If you're trying to make a supercritical fluid out of iodine, you're going to have a temperature up in the hundreds of degrees Celsius. So if you tried to use that to decaffeinate coffee, you'd be cooking the coffee beans, right? You want to roast them, but you don't want to roast them too much, right? And so that's one of the beautiful things about supercritical CO2 is its critical temperature is at a reasonable temperature. But down here is 1 atmosphere, normal pressure. So if you take solid carbon dioxide and you just change the temperature without changing the pressure, there's no liquid there. It's just sublimation. There is no temperature at which liquid carbon dioxide occurs at 1 atmosphere of pressure. Doesn't happen. You have to get to a much higher pressure before the liquid will occur. Any questions?
So it takes a lot more pressure to change than it does for temperature if you want to change states?
Yeah, the slopes of the lines are going to be different, and so some substances are very sensitive to temperature changes, some are very sensitive to pressure changes, some are kind of in between. But yeah, that's going to vary from substance to substance. Over here for water, we're looking at pressure differences, here down at 0 up to 1 atmosphere. So this diagram for water is all in this area, all in this region down here. Well, actually it's around here, right? And so that's in the range where CO2 is a gas, period.